Welcome to the lecture series on IC applications. Myself, Sivaramakrishna, Department of ECE. In this lecture, we will continue the discussion on operational amplifier. Today, we are going to discuss the characteristics of operational amplifier. So, we know the characteristics of characteristics of any electronic device, such as if you consider a diode, so what it is going to have? If you want to study the electrical operation of a device, what is required here? We need to understand the characteristics of any device. So it can be a diode, or it can be a transistor, whatever it may be. So basic thing is we need to understand the relation between V and I, where V stands for the voltage and I stands for the current. It is required to know the relation between voltage and current, how the voltage and current are varying across the device. That we need to understand to study the behavior of any electronic device. Similarly, we are going to study the characteristics of operational amplifier. So the objective of this lecture can be noted as to familiarize with AC characteristics. One can surprise with the term AC. So if you remember the characteristics of any diode or transistor, what will you summarize? So if you consider a diode, you want to study the characteristics. What are the characteristics you will note here? So you will say that forward characteristics and reverse characteristics, that is forward bias characteristics as well as reverse bias characteristics. These are the two characteristics to be required to understand the operation of the diode. Similarly, if you want to study the operation of a BJT, that is a transistor, what is required here? We need to study the two characteristics. What are the input characteristics and output characteristics? Again, whether it is input or output, irrespective of the nature, we are going to find the relation between V and I. We are going to find the relation between voltage and current through the device, right? And here, in operational amplifier, these characteristics are summarized as, it is not a summary, in fact, that is a nature to study the operation. If you want to study the operation of operational amplifier, we need to understand the AC as well as DC. One should know the AC characteristics as well as DC characteristics as well as the AC characteristics of operational amplifier, that is op amp, what we are going to call it as op amp. So in summary, the characteristics are categorized into AC characteristics as well as DC characteristics. The way you coin the term, that is input characteristics, output characteristics, if you are dealing with a BJT. Similarly, the term, that is forward bias characteristics as well as reverse bias characteristics in the case of a diode. So here we are going to discuss both these characteristics, that is AC characteristics as well as DC characteristics. First we are going to discuss the AC characteristics. So the objective is this one, to familiarize the AC characteristics. What are the AC characteristics? Again, so it is very specific that we are going to discuss the AC characteristics as well as the DC characteristics. And what are the parameters to be considered while discussing AC characteristics? You just think sometime, what is AC here? The entire operation is all about the sinusoidal signal. By applying some sine wave input, you are going to study the behavior, or you are going to note down the operation of your operational amplifier. So while giving a sinusoidal input, how it behaves? how to characterize the behavior of the operational amplifier by applying a sinusoidal input. It is required to note down the frequency response. We need to determine the frequency response of particular input. How it is varying? What is varying here? Output. For a given sinusoidal input, what kind of response we are getting? What is your output for a given Vin? Here Vin is nothing but your sinusoidal input. And what is the nature of your Vout? What is the nature of your Vout at different frequencies? At different frequencies, this is called the frequency response. How the amplitude of the output, that is how the output of your operational amplifier is varying in according to the variations in the input frequency. So we are keep on varying the term called frequency. We are going to vary the frequency term and we will see the response in terms of the output, in terms of the output voltage. That is called the frequency response, right? So this is a parameter to be considered to study the AC characteristics here. Apart from once you know the frequency response, you can always determine the another term, that is bandwidth, and you know how to determine the bandwidth. How to determine the bandwidth? By knowing F1 as well as F2. What are F1 and F2? That is the lower cutoff frequency as well as the upper cutoff frequency are considered as the two corner frequencies. So once you are ready with the frequency response, then you can determine the bandwidth by knowing the two corner frequencies, that is lower cutoff frequency as well as the upper cutoff frequency, right? And the other parameter considered here is the slew rate. One more parameter to understand the AC characteristics or the AC behavior of the operational amplifier is the slew rate. For a small variation in the input signal, how it is responding, how the operational amplifier is responding in terms of the output for a small signal, of course it is again going to be the AC signal, right? So in this we are going to see the frequency response, how the frequency response is going to affect, how the input signal is varying, how the input signal is affecting the output. Output is not going to be constant, right? So as we vary the frequency, you can see the change in the amplitude of the output signal, right, with respect to the frequency by varying the frequency. So input is given which is supposed to be constant, and how the output is varying, in according to the frequency. However, the input signal remains constant, right? Now see here, how can you determine the response, frequency response? So the direct answer is vary the frequency, keep the input voltage constant, and see the changes in the output voltage. So once you are ready with input voltage and output voltage at different frequencies, so say here is your frequency, and here is my Vin, and here is the Vout. So what we are going to do? Vin remains constant. There is no change. Vin remains constant for all the frequencies. Let us say at 100 Hz and 200 Hz, and let us say some 1 kHz. Or you want to move up to 10 kHz. Vary the frequency, keeping the input voltage constant. And here you will see the changes in your output voltage. You can note down the changes in your frequency, changes in your output voltage. So once you are ready with the output voltage as well as the input voltage, you can determine the parameter called gain. That is called gain. What is the gain here? Gain is nothing but the Vout by Vin. That is the ratio between output voltage to the input voltage. So this is what? Gain magnitude. Of course, what is the magnitude? We always interested in calculating the magnitude of the gain, which is expressed in terms of decibels. And the other parameter that is calculated from the frequency response is going to be the phase angle. What is the phase angle between the input and output at different frequencies? right? And we are going to investigate whether it fluctuates, whether the phase angle, how the phase angle is fluctuating. Again, the phase angle will never remain constant for all the frequencies. It will fluctuate. You can see the variations in the phase angle at different frequencies. Will fluctuate to differences in the operating frequencies. So both gain as well as the phase angle will vary. Both the gain as well as the phase angle will vary according to the changes in the frequency. So this is the reason it is called as a frequency response. So which parameter we are going to vary here? Frequency. By varying the frequency, we want to determine the changes in the magnitude as well as the phase angle, which is considered as a frequency response. The frequency response describes how the gain of the operational amplifier is going to have changed. How the gain of the op amp reacts to various different frequencies. At different frequencies, how the gain is varying. That's what we said. Frequency response means it is about the frequency versus gain and frequency versus phase angle. It is a difference. It is what? How the gain is varying with respect to the changes in the frequency. And so this is nothing but the open loop gain or closed loop gain. You do come across these two terms here in operational amplifier, because here we are going to establish a connection between output to input. There is a tapping point between the output and input. This always considered as a feedback. Without feedback, the gain is measured is going to be the open loop gain. With feedback, if you measure the gain, it is going to be the closed loop gain, right? When the specific frequency is achieved, the op amp gain diminishes, nothing but the roll off. So this is another important behavior, roll off. Since it does so at higher frequencies, the corresponding circuit of the op amp must have a capacitive component. So if you find any such behavior, you need to incorporate a capacitor. If roll off occurs, we need to introduce a capacitor in the circuit configuration of your operational amplifier. So you just remember a few terms. That is what is meant by the frequency response. How you are going to calculate or how you are going to determine the frequency response, right? So you just remember these two things. What is meant by the frequency response and how we can calculate the frequency response. So simply remember, it is a frequency versus gain as well as frequency versus phase angle. Both will fluctuate. And how far they are fluctuating at different frequencies, that we are going to measure. Okay. Now here we are going to present some equivalent circuit of an op amp to determine the frequency response, right? It is an equivalent circuit. Having input port and output port. See, operational amplifier is also an amplifier. It is not something different. And we all know that amplifier has two ports. What are the two ports? One is the input port and the other is going to be the output port. It is going to have input port and output port. So keeping that idea in mind, we can draw the equivalent circuit of operational amplifier with input port as well as the output port, right? Now see here what you can observe here. So how many inputs are required for operation here? So op amp will consider two inputs. In general. So here we have two inputs, that is I can say V1 here and V2 here. In other terms, they are nothing but the inverting input and non-inverting input. Let us consider both are active. Okay. And coming to the output, and in the input we have one more parameter, that is called RD. What is this RD? Nothing but some input impedance. We can say definitely there will be some input impedance present in the input port. And what is VD here? VD is supposed to be the actual input signal obtained by performing difference, obtained by measuring the difference between the two input signals. What are the two input signals? V1 and V2. That is inverting input and non-inverting input difference, which is applied to the operational amplifier. So this is these are some components considered in the input port. Coming to the output port, what we can consider in the output port here? You can see that there is, we already said the capacitor requirement. If there is any roll-off category, roll-off phenomena occurs, then it is always better to have that particular capacitor. Okay, and we have an output resistance R0. And you can see some current source here. We can see some current source. It is in the general nothing but the voltage source. It is nothing but a voltage source across the output terminals. That is AOL V1, where AOL is nothing but the open loop gain. Open loop gain of the operational amplifier. And V1 is of course going to be the input voltage. That is generally the difference voltage. It is not V1, actually it is supposed to be the difference voltage. AOL VD. Okay. So because unlike the traditional amplifier, here the input voltage is not 1. Okay. It is not one term. In the input we have two voltage terms. There are two input terms. It is always better to consider both. The difference between the two input voltages. So we can say that this is going to be the VD. So this is the simple what we can say equivalent circuit to measure to perform the frequency response or to analyze the frequency response. See what we are going to measure under frequency response. What is the output voltage for this difference input? And you keep on varying the frequency. At different frequency values, what is your output voltage? And also we are going to determine the corner frequencies. We are going to determine the two corner frequencies, lower corner as well as the upper corner frequencies. So preferably it is going to be the single corner frequency. Okay, because I will tell you why we are going to have single corner frequency. Why can't we have multiple? Can I have multiple corner frequencies? Yes. It is all about your circuit configuration, or it is all depending on your circuit components. How many capacitors are there? How many RC components are there? Here if you measure, if you see here, this is nothing but RC network. So whatever we are measuring the corner frequency, it is purely because of this RC configuration. Okay. And also determine the open loop voltage gain. So you must know what is meant by open loop and closed loop. Open loop voltage gain means without considering the open loop voltage gain is what? Without considering, without feedback. Without feedback. Without feedback, if you start determining the gain, if you measure the gain without feedback, if you measure the gain, that is called, what is it? That is called open loop gain. With feedback, if you measure, it is called closed loop. It is called closed loop gain. So this open loop gain is usually denoted as OL. That's what we said, AOL. And closed loop gain will be denoted as ACL. Try to remember this terminology. So AOL represents the open loop gain. That is without considering the feedback. And ACL means with feedback. That is supposed to be the closed loop gain here. Okay. And now see some important observations. What we can do here. See, in frequency response, we are going to determine the corner frequency. Of course, anyway, we will get the gain. By determining the output voltage, one can determine the gain. Gain across the frequencies. Right. So, the gain magnitude for frequency F1. Generally, how we will denote the gain here? So, tell me, gain is a unitless parameter or unit parameter? It is a unitless parameter. If whatever the gain you consider, if you say voltage gain, if I say voltage gain, how will you represent the voltage gain? It is nothing but V out by V in. It is the ratio between the output voltage to the input voltage. If I say it is going to be the current gain, what will you say current gain? It is I out by I in. Right? Now look at the numerator and denominator. What are the units for numerator? Volts. What are the units for denominator? Volts. So no unit here. Similarly, if you consider current gain, what are the units here? Amperes. And here also the denominator, what are the units? Amperes. No units. Right? These are the actual values. These are the actual values of the gain. But in the analysis, in most of the cases, we represent the gain in terms of the decibels. In terms of the decibels. That is nothing but dB. So how to calculate the value of the gain in decibels? It is nothing but 20 log. Put the actual value AOL. 20 log of AOL. This will give you the gain in terms of the decibels. Let us say this is the gain measured at F1, a corner frequency. And so once you determine the frequency response, of course you can remember this type of curve. So because this we can determine especially for the amplifiers, nothing but the frequency response. So what we have on the x-axis, it is going to be the frequency, and y-axis is going to be the gain. Y-axis is going to be the gain here, right? And in order to determine the lower and upper cutoff frequencies or corner frequencies, how will you measure the corner frequencies? With the help of the 3 dB. With the help of the 3 dB, that is maximum gain minus 3 dB. Maximum gain minus 3 dB. Suppose the maximum gain is, let us say 50 dB you are getting. And you will measure the 3 dB at 47 dB. You will measure the 3 dB, that is at 47 dB. At the 47 dB, we are going to determine the corner frequencies. That is F1 as well as F2 we are going to determine. Are the two corner frequencies. Right, and there is the relation, that is F greater than F1. So what is F1 here? F1 is the lower corner frequency and F2 is nothing but the upper corner frequency. And what is the scale here? The entire scale represents a frequency. The entire scale represents a frequency. See, up to here, what will you say? F is less than F1. F is less than F1, that is the actual frequency F is less than the corner frequency F1. And beyond this point, what will you observe? The actual frequency is greater than F1. The actual frequency F is greater than F1, right? And if this instant occurs, one can experience the decrement in the slope, the decrement in the curve. See, this is what we are observing here. What happened to the curve here? This is decline. Understand? With some slope, the curve is being reduced. The curve is being reduced with some slope. The slope is going to be the minus 20 dB per decade. Minus 20 dB per decade you will notice actually. Right? So over F greater than F1. So this curve is because of the phenomena, that is minus 20 dB per decade. Since you have only one RC network, if you have multiple RC networks, accordingly the curve will drop with some slope. It can be minus 40 dB per decade or it can be minus 60 dB per decade. It all depends on the number of RC components we have in the network. The number of RC networks present in the circuit. Okay, so this is another observation we can find here. And in summary, if you want to plot the frequency response, here you can see 20 dB per decade. And what happened here? This is what after and before. You can see that this is the corner frequency F1 up to the corner frequency. What is the nature of your curve? And after corner frequency, what is the nature of your curve? You can clearly notice that there will be a drop. There will be a drop after, that is when the actual frequency F is greater than F1, one can notice there is a declination, there is a decrement in the curve with some standard slope, that is called minus 20 dB per decade. Minus 20 dB per decade you can observe. With that the slope is being reduced or dropped. Okay. And now coming to the phase response, coming to the frequency response in the context of the phase angle. So what is meant by the frequency response? The variations in the frequency and gain. Similarly, the variations in the frequency and phase. So whatever we observe here, up to now, it is purely the relation between F versus gain. It is purely the relation between F versus gain. How the gain is being changing or varying with respect to the changes in the frequency. Now we will see the phase angle. Even in the phase angle also, you can notice the declination or decrement in the slope of the curve with some standard value, that is 20 dB per decade, or it can be minus 40 dB per decade, or it can be minus 60 dB per decade. There is every possibility, right? And of course, this is an example for gain. I'm sorry to say, this is an example for gain. Okay, so how the gain will drop? How the gain will drop as you increase the number of RC networks. If you have only one RC network, you can expect one. If you have multiple, you can find multiple corner frequencies. See here, F1 is there, F2 is there, and F3 is there. And at F3, when F is greater than F3, what you can sense here, there is a declination in the curve with some standard slope of minus 60 dB per decade. And when F is greater than F2, you can notice the drop in the curve with some slope value, that is minus 40 dB per decade. And what we have seen, when F is greater than F1, you can see the decrement, you can see the declination or in the slope with a value of minus 20 dB per decade. Similarly, you can draw the phase angle versus frequency. How the phase angle theta is varying with respect to frequency. It indicates an op-amp may have a maximum phase change of 90 degrees when it has a single capacitor or multiple, or see below. Again, the phase angle changes also depends on your RC network, right? So the nature of the frequency response is purely depends on how many number of RC components are there, RC networks are there. How many are there? Maybe there is 1 or 2 or 3 or maybe more, right? So whatever we have seen, that is AOL with respect to the open loop. We haven't considered any feedback there. Now, if you observe the circuit, here we have a feedback path. So this is called a feedback path. You can notice there is a tapping point between the output as well as the input, output to the input. That is, from the output, we have a connection to the input. That is, a part of the signal is sent back to the input. So why we are doing this? Why we are doing this in operational amplifier? The reason is same. So what we can say, circuit stability. Then when compared to your normal amplifiers or basic amplifiers such as common emitter or common base or common collector or any FET amplifiers, these operational amplifiers are very stable, in fact, right? So let me coin the term stability. What is by stability? Stability represents the how much the gain remains stable. So we never expect or we never experience fluctuations in the gain actually. We will try to avoid, we will always avoid such fluctuations in the gain because we want a stable gain. That is always possible with the help of a feedback path. That is the purpose of the feedback path. So the circuit stability can be achieved by using your feedback path. So this you might study it in feedback amplifiers. In feedback amplifiers also, we have two types, right? One is a positive feedback and other is negative feedback. So if you remember the negative feedback, so what are your negative feedback? They have more stability when compared to the positive feedback. In fact, positive feedback are nothing but oscillators. So this feedback is supposed to be negative. You can notice here, this is a negative feedback. In order to improve the stability, if you want to improve the stability in your circuit, especially in amplifiers, better incorporate the negative feedback. If you have a positive feedback, what will happen? It will fluctuate, it will continuously oscillate, nothing but the oscillator, right? I hope you know about it. So circuit stability can be achieved by considering the negative feedback rather than the positive feedback. Positive feedback leads to oscillations in the output, behaves like an oscillator. Here you can see some expressions here. So AOL, this is nothing but AOL stands for open loop gain at certain frequency. At some frequency is always represented as V0 by Vin. Whatever we said, gain is always the ratio between output voltage to the input voltage, right? And AOL for the closed loop, is given by, this is nothing but ACL, closed loop gain. What we are going to say, it is nothing but AOL by 1 plus AOL beta, right? This is because of that negative feedback. This is because of your negative feedback we are getting this particular expression here. Okay, so now, so this is one way to understand the AC characteristics. So what are AC characteristics? AC characteristics are nothing but the frequency response. What are frequency response? What is frequency response? That is finding the relationship between frequency versus gain. Frequency versus phase angle. How the gain is varying with respect to the frequency. How the phase angle is varying with respect to the frequency is called the frequency response. And one must calculate the expressions for gain. And here we have seen open loop gain as well as the closed loop gain. Both we have seen here. Right? Open loop gain means without considering the feedback, and closed loop gain means with considering the feedback. So we said the other important parameter in AC characteristics, nothing but slew rate. Slew rate. Let us see what is the slew rate. The slew rate in any electronics, in any device, can be simply defined as the rate of change of output voltage of the op amp for each unit time. See, it is just like a generalization. How, with what rate or how much rate the output voltage is changing. The output voltage is changing for a specified unit time. For a specified unit time, how the output is changing. It is generated as a what we can say slew rate. So you can see the term rate. So whenever you find the term called rate, what it means, you will see in the denominator, that is time. You will see in the denominator, that is time, some seconds. That is what your acceleration. What is your acceleration? What is my acceleration? Rate of change of velocity. With what rate? Or how much rate the velocity is changing with respect to the time here. Similarly, slew rate is the parameter. It is used to define your performance of your operational amplifier. In another way, one of the important AC characteristics. So what it is? The rate of change of output voltage per time in a given specified time, that we will say, right? And it is denoted by the term called S. Do you remember? Slew rate is denoted by the term called S, denotes the slew rate of an op amp. So what is the significance of this slew rate? How it is important in the operational amplifier analysis or to understand the op amp behavior? The two AC characteristics. See, the highest input frequency. It helps in identifying the highest input frequency and amplitude that are suitable to the operation of your amplifier, right? See, if somebody given you an operational amplifier, what rate, how far you can work on this? Actually? What is the benchmark? With what frequency I need to proceed? Where I need to stop the analysis? So this parameter will help you in identifying so what is it? Highest frequency, highest input frequency as well as the amplitude that are suitable for the effective operation of your operational amplifier without damaging. See, like any other device, op amps also will burn. Op amps also will get heat up. So simple. If you change the bias, that is, you know that op amp is going to have two bias. One is a positive bias and the other is negative bias. Both are there. VE as well as a VCC. Both are there. You just reverse these two bias, you can see some change in the heat. You can see the increase in the temperature within the device, and this will surely burn actually. right? So to avoid all such things, we must know what is the highest frequency as well as the highest input amplitude with which one can operate the amplifier, operational amplifier, without any major damage, that I can see, right? So the slew rate must be high. So what is the value of S? What is the value of S? Whether it should be high or is going to be the low. It should be minimum or maximum. So this is what the comment. The slew rate must be high to ensure the highest undistorted output voltage swing. To ensure high undistorted output voltage swing, better to have the high slew rate. And it is used to verify whether op-amp can deliver a reliable output. A reliable output to the a reliable output for a given input or not. Right, this is again another significance of the slew rate. Do remember, it should be high. So what are the significance means? It helps you in determining the reliable output, right? And the factor will be changed once the voltage gain is changed. So what is the meaning here? This is sensitive. This is sensitive towards the gain. Slew factor is sensitive towards the gain. Whenever there is a change in the gain, the slew rate will change. So do remember this point. So usually these things are specified in the conditions, right? In the conditions that you may have the unit gain, or below that or above that you may have. So whenever you vary these gain values, the slew rate will vary. Okay, for instance, if the general purpose op-amp slew rate value is 10 volts per microsecond, the value of S here we are specifying is S is equals to, we say 10 volts per microsecond. So say this is at the beginning. This is say at the beginning we have this value. This is the value at the beginning. Now what happened? What happened when large step input signal is applied? See, the operation of the slew rate can be studied by inputting a step signal. You can test the operation by inputting the step signal. Right? Is given at the input, then the device can generate 10 volts. Can generate 10 volts at the output within 10 volts at the output within what time? You can see that 1 microsecond. That is what the meaning. 10 volt per second per microsecond. 10 volt per microsecond. What is the meaning here? This is the rate of change of. Understand? So it can change the output value. It can change the output value to 10 volts within a period of how much time is required to reach the 10 volts here? This is what the representation, within a fraction of microseconds. That is the meaning here. Okay. So the slew rate formula, try to remember the expression here. It is going to be the del out by del T. Del V out, that is nothing but the output voltage to the rate of change of time generally. So you measure the output voltage at T1, you measure the output voltage at T1, and you measure the output voltage at T2. You measure the output voltage at T2 and see the comparison, see the difference. V out is nothing but V out at T2 minus V out at T1. So this is the general practice which we will consider while measuring slew rate here. So remember, what is the definition? The definition for slew rate, what is the significance of the slew rate? How it will describe the performance of the operational amplifier. So only thing is reliability in the output, and you can find how safe it is, and you can see the changes in the output voltage within the time you can see the changes in the output voltage. Okay, and now this is what the circuit we can see here. So you can see the input here. This input is nothing but seems to be a square signal. It is a square signal, I can see, or a pulse. So generally, what are the characteristics of the square signal? It is going to have two levels only. What are the two levels? One is the upper level and the other is the lower level. So with these two levels, the signal will propagate actually. So one is going to be the lower level, then this is going to be the upper level, and this is going to be the lower level. So how much voltage changes? How much voltage changes with what time? When the level changes. When the level changes. So what are the level changes here? From lower to upper, and similarly from upper to lower. from upper level to lower level, similarly from lower level to upper level, when the signal transition occurs. So what is the nature of your output voltage? What is the nature of the output voltage in a given time, within the time specified, in a given time? That is, here T is very, very important. And how much time it is required? How much time it is required to reach the specified value, to reach the specified output voltage? Okay. So this is the circuit we consider here. And this is how the operation. So as we said, no, it is all about the signal which we are applying. Generally, slew rate, if you want to measure the performance of the slew rate, the correct measure is always input the square wave. Input the square wave and see the changes in the output voltage. See the changes in the output. So basically, we use a CRO to see the output voltage. To see the output voltage, how this Vout is changing. How this Vout is changing with respect to the Vin. That is from low level to high level, as well as from high level to low level. What is your output voltage and time? What is your output voltage with respect to the time? So this we generally consider to measure the slew rate, right? So these are the two important characteristics of operational amplifier, nothing but AC characteristics. So what we studied here, one is the frequency response, and the other is the slew rate. Under frequency response, we measure the gain, that is the frequency versus gain, as well as frequency versus theta, that is phase angle, right? These things we have seen in this, we have seen up to now. Now in the next class, we will focus on the DC characteristics of the operational amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.